Alright, this is Physics 1C for October 8th. Tonight we're talking more things about magnetism. We're going to start off with refreshing what we did last time. Last time what we talked about was that there's this idea of something called a magnetic force, and that it's equal to this expression here. And the idea is if you have a charged particle and it's placed into a magnetic field, if it's not moving, it doesn't feel a force, but if it has a velocity, then it feels a force that's at right angles to both the velocity and the magnetic field. And one of the examples that we discussed last time was if you have a magnetic field that points into the board, we use these little X's to represent a vector that points into the board. So if that's our magnetic field, and we have a charged particle, and it travels, let's say, with a velocity that's exactly perpendicular to the magnetic field, then we said that that's going to create a force on the particle. You use the right-hand rule, where you point your fingers in the direction of the velocity vector, and then you rotate them with your palm downwards towards the magnetic field, and you get a force that acts kind of up like this. And the effect of that is that it's going to cause the particle to travel in a kind of circular path like this, because the velocity and the force are at right angles to each other. And we said that we could find the radius of such a path, r, by taking basically the momentum of the particle divided by the product of the charge and the magnetic field. So that's the last thing we did last time. Did anyone have any questions about all that? So I thought it might be a good idea before we go into something that's more complicated, which is what happens when it has a velocity that's not exactly at right angles, to look at a demonstration of this. So I found this video. I found a few different ones, but this one seems to be really good at showing you kind of what's going on here. So I'm going to do this. I have to switch what I'm sharing. Because he is going to explain some things. Okay, I'm going to just check to see that you guys can hear it. Can you guys just say if you can hear it or not? Okay. All right, we'll start at the beginning. It's kind of dark, so... Okay, anyone have any questions about that video? How do I get this to stop playing this? So we actually have that whole apparatus that he's showing there in the picture. This thing with these two coils like this, we have these at the school. And there's a lab that y'all do, or would have done, if we were there in the spring. That works exactly the same way, where you basically just... what you end up doing is you actually end up measuring the Earth's gravitational, or not gravitational, you measure the Earth's magnetic field, actually, because the way that the one that we have at the school is designed is that this whole apparatus right here is capable of like being lifted up and down from like 0 up to about 60 degrees, if that makes any sense. So you could imagine that this thing, when you walk into the room, the thing is flat. And what happens that's really kind of interesting is that when you turn on the beam, like he does here, it looks, I mean, it looks exactly the same, by the way. Where's his beam? Oh, there it is, that beam. When you turn the beam on, when you first have it set up and it's flat, you immediately notice that the beam already starts to curve a certain way. And it curves because the Earth's magnetic field affects it, which is kind of wild. So what you end up doing is you have to kind of correct for the Earth's magnetic fields. And then you have to get it to go perfectly in a circle and hit these pegs. And you end up measuring, well, this is where I'll switch screens back to the main screen. You end up measuring the radii. Change windows, right? There we go. So what you end up doing is you end up measuring, where is it? Here we go. You end up measuring the radii of different paths. Oh god, I hate when it does that. You measure the radius here, and what you end up also measuring you measure this, and you use that actually to calculate the mass to the charge ratio. And because the particles are electrons, what you end up doing is converting or calculating what the mass of the electron is divided by the charge of the electron, which is a pretty powerful thing to be able to do, to measure something so tiny by that kind of big apparatus right there, because the electron mass is really small. Anyway, so that's an example of this phenomenon that we talked about last time, of a charged particle placed into a magnetic field that undergoes this perfect circular motion. It's pretty neat. What we're going to do now is we're going to look at what happens if that velocity vector is slightly tilted. So imagine that this vector, if you were to pull it up out of the page towards you, and we want to think about what's going to happen. So this picture right here is a visualization of what happens. I tried to find a video of this, of a particle actually doing this, and I couldn't find an actual video. I found several animations, and we can watch one. But so in this case, what happens is that you've got a magnetic field. It's pointing along the x-axis, right? We already know that these charged particles want to take these circular paths around. But what if the particle has a velocity vector that's parallel to the magnetic field? We know that the magnetic field, whenever you have a velocity that's parallel to it, what happens? If you have a velocity component that's parallel to the magnetic field, what does this equation tell you about the force in that direction? Like in this case, in the x direction. No force, exactly. It's only the component that's perpendicular, which is displayed here by this v perpendicular. And so the effect is that basically in this type of a picture, the horizontal velocity along the x direction is going to be constant. And so as a result, if you take the circular motion and you add to the circular motion a translational motion, the path you get would be like a little spring or a helix like this. Is that something y'all can visualize? Do you want to look at did I keep it? Yeah, okay. Do you want to look at what this visualization is supposed to show? This is a really long video, and I didn't find the video itself to be particularly useful. Maybe you would. But it kind of just shows... Oh, you guys can't hear this, right? I don't think you can. He's really loud. Any questions? Go ahead and ask questions if you have them. People are typing. No? Okay. So I was going to say, we can visualize this at some point in this video here. There we go. This is kind of what the motion looks like. This little coil kind of moving around in a circle like that. Does that make sense? We're going to do a problem where we do some calculations with it. Okay. All right, so you notice in a way that magnetism is a really good way of capturing particles, right? And this helical motion like this, it turns out is what's responsible for what's called the Aurora Borealis, or the northern lights. And kind of the way that works is that the Earth, we said, has a magnetic field, and the magnetic field is such that it can kind of trap particles coming from space. So if this is the Earth, we said that it has this magnetic field where it's almost like a bar magnet, and the bar magnet is kind of situated such that the northern pole of the Earth is the southern pole of the magnet, and the southern pole of the Earth is the northern pole of the magnet, but it does have a magnetic field. And what will happen is that charged particles coming in from space will come in this direction here, and they'll basically spiral in. I have to think about this for a second to make sure I get the direction right, but you can imagine that particles coming from space are going to have this type of motion too. And they come in, they interact with the atmosphere, they lose a little energy, and they tend to spiral in. And then when they collide with the atmosphere itself, those collisions produce these like really bright phosphorescent lights and stuff, and streaks of patterns throughout the sky called the northern lights or the Aurora Borealis. And if that's something you haven't heard of before, I mean, I've never seen these before. I've only ever seen pictures of them, honestly. But they look maybe, something like this. I don't know, we have an ad for 4 seconds, but when I say the northern lights, is that something you've heard of? There's also the southern lights. Have y'all heard of these before? Okay. This is in February of 2014, strong aurora activity. Let's get to the... So that's what they look like, apparently. And that must be... I mean, it kind of looks cool on the screen, but I'm sure it looks way more impressive in person. Has anyone here ever seen these before? You have to go really, really far north, like to Alaska or to like Scandinavia. I've never been to these places, but look at that. It's like red and green. It's literally just charged particles being sucked in and cascading down through the atmosphere. Particles from space. It's very science fiction-y kind of in a way. All right. So, all right. So what we want to do is we want to kind of look at a problem that analyzes a situation like this. And that's this problem right here. So hopefully you can read the problem okay. It says, in a situation like the shown in the picture here, the charged particle is a proton, so they give us the charge and the mass of the proton here. And the uniform 0.5 Tesla, this is how magnetic fields are measured, is directed along the x-axis. It says at t equal to 0, the proton has velocity components that are given by these numbers here. So it has an x velocity, x component of velocity that's 1.5 times 10 to the 5th, a y component that's 0, and a z component that is 2 times 10 to the 5th. So really, all of its motion is in the x and z directions, at least momentarily. So where would that be on this picture if it's going around like this? If the z velocity is positive, the x velocity is positive, would it be kind of up here at the top? Would it be down here at the bottom? Can you visualize what that means? The vy is 0, vz is this. Don't worry about the exponents, just think of it as vx is like 1.5 and vz is 2. Where would that be on this little picture here? Would it be down here at the bottom when it's going out? Would it be on the side when it's going up? Would it be on the top when it's going that way? Where is it in the motion? Did that question make any sense? If you need time to think about it, that's okay. I know it's pretty hard to visualize these three-dimensional things. On the xz plane, yeah, so it's at the bottom, right? It's down here at the bottom, where it has, it's got a component of its velocity that's kind of coming out of the board, or along the z-axis. I guess if we were to draw it in here, it'd be kind of, let's use, what will stand out the most, maybe this purple color. Probably easiest to draw down here. So it's kind of like, its motion, it's like this way. That's like the vz component, right? And then you've got a vx component that goes that way. But the y component is 0. The component that would be parallel to this axis right here is 0. So it's down there. That's time equal to 0. At that moment, we want to find the force on the proton, as well as its acceleration. And then we want to find the radius of the resulting helical path. We want to find the radius of this path. That could be indicated as, is a different color maybe? Black. The radius would be like from here down to there. That's like the radius. We want to calculate what that is. And then we want to find the pitch, which is going to be the distance traveled along the helix per axis of revolution. So that's going to be basically like the distance in this direction here. We'll call that the pitch. Maybe it's like delta x or something like that. So those are the three things we want to find. We want to find the force, the acceleration, that's part A, and then we want to find this distance delta x and the radius r here. Okay. So let's try to do that. So this is where our force is going to come from in this problem. The only thing that exists here is just the fields, the magnetic fields, and the proton that's moving through it. So we want to use this equation here to find our force for part A. All right, so we have charge. We're given the magnetic fields right here. And we know the components of the velocity vector. So we'll say that the force is going to be equal to the charge, which is 1.6 times 10 to the negative 19, multiplied by v cross b. So right here we'll write the velocity in component form. So it would be something like 1.5 I hat. I'm going to put the exponent at the end, plus 0 j hat, plus 2 k hat. And then that's times 10 to the 5th. And we have to multiply that cross product with b. So I'll just put times 10 to the 5th out here at the end. And that was in units of meters per second. And then we'll put the magnetic fields. The magnetic field is 0.5 Tesla, but it's directed along the x-axis, which means we can turn this into a vector by multiplying by I hat. So this would be cross product now with the magnetic field vector, which is 0.5 Tesla times I hat. So we just need to calculate this out here. All right. When we do the cross product of 1.5 I hat with 0.5 I hat, what are we going to get? What do you get if you do I hat cross I hat? And does anyone want a refresher on what I hat, j hat, and k hat are? This is equal to 0, that's right. Does anyone want me to... I don't mind doing it real quickly. They're just unit vectors. If you make your xyz plane like this, x, y, and then z coming this way, then unit vectors point, they have length 1, I hat goes that way, j hat goes this way, k hat goes this way. Probably be better to call them x hat, y hat, and z hat like a lot of other textbooks do, but it's not a big deal. When you do I hat cross I hat, in fact, when you do literally any vector cross with itself, you get 0, and the reason why is because to do the cross product, you would do 1, the magnitude of this vector, times the magnitude of this vector, times the angle between them. You have to take the sine of it, and the sine of 0 is equal to 0, so that's why this is equal to 0, and any vector cross with itself. Okay, so then we have... I hat cross I hat is 0, so it's really only this term. 2 cross 0.5, well, 2 times 0.5 is 1. And then k hat cross I hat, what's that equal to? What's k hat crossed with I hat going to be equal to? There's some rules of these, and maybe you remember what they are. Is it j? Yeah, it's j, right? It's going to be j hat. You can figure that out by using the right-hand rule. You point your fingers kind of out of the page like this, of your right hand. You face your palm towards I hat, and you curl your fingers, your thumb points up, and that gives you j hat. Okay, so we multiply this all out, and our answer is going to have a j hat in it. The units are going to be newtons, and we already said that this cross this is 0, so you just have to do, let's see, 1.6, so it's pretty easy to do this, right? It's going to be 1.6 times negative 19 and 5, you're going to get times 10 to the negative 14. And there we go. I think that's the answer. It's positive j hat, which means it points upwards, which is what we want here. It's going to point, and I almost don't want to draw it on here, but it's the velocity vector is pointing, or sorry, the force vector, excuse me, is pointing straight up along the y direction, basically, down here at the bottom, which is going to allow it to then curve as we want it to. Okay. That was the first part, to find the force. They also want us to find its acceleration as well. Once we know what the force is, then finding the acceleration means we just take the force and we divide by what? If there's only one force and I want to find acceleration, what do I have to divide? Just by the mass. Right, so then the acceleration is going to be equal to that force, 1.6 times 10 to the negative 14. And I guess this is technically an acceleration. Newtons times j hat divided by the mass of the proton, which is 1.67 times 10 to the negative 27 kilograms. This is pretty clearly going to give us a really large acceleration because we're doing all. Oops. Okay, 14. Oh, what's this going to be? Can you guys calculate this for me? It's going to be pretty close to 1. (27 minus 14). 13? That makes sense. So it's a little bit less than. So about 9.6 times 10 to the 12th. Thank you. And then just we'll put out here meters per second squared. It's a really big acceleration, right? Okay. So it's a centripetal acceleration, though. So this acceleration is actually not going to change the speed of the particle at all. The speed of the particle will end up being, well, constant in this case. The speed will always be the same because the magnetic field can't actually do work to increase the speed of the particle. It can only change the velocity of the particle. Does that make sense? The force is always perpendicular to the velocity. It's like guaranteed to be. So if this is the only force acting, it can't accelerate anything other than to change the direction. Sorry, it can't change the speed. That's what I mean to say. Okay, that's part A. Anyone have any questions? All right, so part B, a little trickier. Find the radius of the resulting helical path. So for this, we can use the equation that we derived last time, which is that the radius is going to be equal to the mass multiplied by the velocity divided by the charge times the magnetic field. However, when we made this relationship, we specifically were talking about a velocity vector. And this velocity vector has to be basically perpendicular to the field. It's really only the component that's perpendicular to the field that's going to cause this circular motion. So in this case, because the field points in the I direction, and one of our components is in the z direction, it's just this component that we're going to care about here. So for us, this is just going to be v times z. Oops. Not v times z, sorry. It's the z component of the velocity, basically. Does that make sense why that's the case? And it's not like the whole we could find the speed, for example, by doing the Pythagorean theorem, right? Find the length of this vector. Hopefully it makes sense that it's just the z component that we have to consider here. Okay, I made a mistake the first time I did this problem in a class, where I used the total velocity, but then someone noticed that was wrong. So it's just the component that's perpendicular that we care about here. Okay, so what's this going to be? The mass is the mass of a proton that we just used. And then the velocity z component is 2 times 10 to the 5 meters per second. We divide by the charge. And then multiply by the magnetic field, which was 0.5 Tesla. And can you guys calculate what that is? Looks like it's going to be something like 4 times something, because the 2 divided by 0.5 is a 4. 27. It's going to have the same... No. These are almost going to cancel out. 4.2 times 10 to the negative 3. Okay. That'd be in millimeters, right? I mean, yeah, you're right. It's meters for sure. I mean, this would be like 4.2 millimeters. If people wanted to have a better, I mean, it's about half a centimeter. That's our radius. That's a really tight radius, right? And then, okay, that's easy enough. Except this part a little tricky. And I believe you do have a homework problem or two that kind of works off the same type of model. Okay, so the next part was to find the angular speed of the proton. Does anyone remember how we do that from last time? Whoa, whoops, didn't do that. How do we find the angular speed? V over r, that's right, exactly. We're very good at remembering these relationships. So again, it would be the perpendicular component of the velocity divided by the radius that we're looking for. So from this equation, we can see that that quantity would be Vz over r, and it happens to be equal to QB over m, I believe. I'm really sorry about that. I'm sure you guys can see these things. How do I close that? Okay, so, yep, QB over m. We've got all the equations, or all the numbers for that here as well. So put the charge in again, 1.6 times 10 to the negative 19 coulombs. Multiply by the magnetic fields. Divide by the mass. And so what is this going to represent? This is going to represent the number of radians per second, the rate at which it's going in a circle, where one revolution is going to be 2 pi radians, right? All right, so what's that equal to? Looks like it's going to be something like about 0.5 times 10 to the negative 8, 10 to the positive 8. What do you get if you do that calculation? Okay. Does anybody else agree with that number? Looks right to me. Okay, so that frequency is really fast, right? 10 to the 8th radians per second. If we divided this by 2 pi, we would get the frequency. And so say that this number is pretty close to 6, so it's almost 100 million cycles per second this thing is going through. Okay, thank you. Someone else said they got the same. All right, so that's our angular speed. All right. So the last part is to find the pitch, which I said was what it says here. The distance is traveled along the helix per axis of revolution. So that would be like this distance here, which is delta x. Can anyone think how you might be able to do that? So this was radius. What was one of the answers? How can we find the distance that it travels in this direction based on the information we have? You said divide by 2 pi. Divide this number by 2 pi. If we divide this by 2 pi, it's going to give us what's called the frequency. If we do omega divided by 2 pi, we could do that. We'd have revolutions per second. Could be useful. I don't know. What do you think? What do we need to know to figure out how far it travels in this direction? Certainly one of the things we need is the velocity in that direction, right? But if I want to find the distance, I would also need the time, right? So I really just need to know the time it takes to go from, like, let's say here, and then all the way once back around again, right? So if it starts in this position, and then it comes back to that position, and then it does it again, we know that it does that at a rate of about this many radians per second. Yeah, one cycle, right? How do we figure out how long it takes to go through one cycle? This is the number of radians per second. We want period. That's exactly right. So period, in this case, I believe we almost is going to be just equal to 2 pi divided by omega, because it's 2 pi radians per one cycle, and this is the number of radians per second. This will give us the number of seconds per cycle, right? You could work it out as a kind of conversion factor if you want to. This one should have been 10 to the 7? Or you mean the frequency? Oh, okay, this should be 10 to the 7? That seems believable. Alright, so... Wait a minute. Wait a minute. 19... this is going to give you 8, right? But then it's 0.5, so if you move the decimal point over one more, that's where the 7 comes from, I guess? Okay. Alright, so... everybody on board with this number? Or do we need to... Alright, cool. Let's find the time that it takes to go through one cycle by doing 2 pi divided by omega. It's certainly going to be a very tiny amount of time. What do you get here if you do that? 2 pi divided by this number. And then after that, well, once we get the time, delta x should just be equal to the x velocity multiplied by the time. You can do it all at once if you prefer. Okay, so I got, the time is like 1.3 times 10 to the negative 7. That's in seconds. Plug that in here. X velocity was 1.5 times 10 to the 5. And we would just multiply that by this number right here. Then whatever that's equal to. I think I just did it. 0.02 is what I got. 0.01. So it's about 2 centimeters. That's the distance that it travels. It travels quite a bit farther in the x direction than it does in the, compared to the size of its, the diameter of its path, right? The diameter of the path is about 1 centimeter, but the delta x is 2 centimeters, so it's about half, about double, I guess. Okay, there's a problem related to the helical motion here of this particle. Does anyone have any questions? All right. Moving right along. All right, we're now going to talk about 2 different applications of these magnetic forces. One's called a velocity selector, and one is called a mass spectrometer. Okay, so a velocity selector is something that does exactly what it says. It selects out particles with certain velocities, only the ones that you want, and in particular, one velocity. This object is composed of an electric field and a magnetic field. And the electric field is constructed by having plates. So you have one plate that is positively charged to some potential, and this is similar to our parallel plate capacitors that we've used in the past. And you have another plate that is kind of next to it, like this, and this plate is negatively charged. Because of the positive and the negative charge right here, I think I should move this down a little bit. Because of the positive and negative charge right here, that means there's going to be an electric field that's created between the plates. So you're going to have an electric field in this region that points like this. And then what we do is we place a magnetic field in the same region, and I've got to think about this for a second. The magnetic field in this case is going to be pointing into the page. So within this entire region right here, we have a magnetic field that points into the page. This could be constructed by having magnets on the top and bottom, with the north face on top and the south face on bottom. So that's our magnetic field, and I'll just say that it points into the page by just saying V in. So the electric field points to the right, the magnetic field points into the page like this, and then let me move this symbol right here for a second. And then what we have is, on one end there's a slit. Here we'll do just like a line. Oh, it doesn't want me to push it up like that. So on one side we'll have a line like this here, but there's going to be an opening in it. And then on the other side, we're going to fire particles. So we're going to have, let's say, positively charged particles that we're going to fire through here. It could be positive or negative. But we're going to have, like, let's say, a beam of positively charged particles that's going to stream through this region here. And we're going to find out kind of what happens to them depending on their velocities. So imagine that a positively charged particle is sitting right here, and say that it has some velocity vector that we point off in that direction there. Can y'all tell me, what's the direction of the electric force on this particle? What's the direction of the electric force? It's to the right, exactly. So there's going to be an electric force that's going to go this way. And then what's the direction of the magnetic force going to be if you do your the magnetic force is equal to QV cross B. If you do V cross B and use the right-hand rule, what direction does the magnetic force point? So you point your fingers of your right hand up along the page. Your palm is facing into the board. You rotate your fingers from V, velocity, to B, magnetic fields, and your thumb points, hopefully for all of you, to the left, right? So that's right, those of you who said left. So then there's a magnetic force on this particle that goes this way. So that's our magnetic force. And then we could say, suppose that we want to make sure that these particles all happen to be able to travel, if they're coming in this way, we want them to travel straight through, just like that. In order for that to happen, if the particles are coming kind of through the middle right here, then these two forces would have to be equal to each other. If these forces are equal to each other, then the particles would go in a straight line, right? So if the magnetic force is equal to the electric force, then the particles will travel in a straight line. And they'll be selected out of the species of particles we might have here. So the magnetic force is described by QVB. In this case, the velocity and the magnetic field are at right angles to each other. So when we do this, it's going to be QVB times the sine of the angle between the velocity and the magnetic field, which is 90. And then on the right-hand side, the electric force we can find quite simply by taking whatever the charge of our particle is here, Q, and then multiplying by the electric field. It's that simple. So you do Q times E, and then we can say that these Q's then cancel. Sine 90 is 1, and what we end up getting is just velocity times magnetic field equals the electric field magnitude, and then we can say that the velocity of all of these particles that get selected out of our selector are going to have a velocity of the electric field magnitude divided by the magnetic field magnitude. And that's kind of an interesting relationship. It shows us that the units of the electric fields divided by the magnetic field give us a velocity, which is, I don't know, maybe surprising to some extent. You could have worked it out with the units yourself, but I don't know if it would have been something you would have guessed to begin with, right? That electric field units divided by magnetic field give you velocity, but there we go. So what happens if the velocity of the particles is higher than this speed? So suppose some particle comes in here and it has a bigger velocity. What's going to happen to that particle? When you come through with just the right velocity here, the particles go in a straight line. Which one of the forces is going to be bigger if the velocity gets bigger? Will it be the magnetic force or the electric force? Which force changes when we change the velocity? The magnetic force is the one that changes, yep. So if the velocity is bigger than this, so if the velocity of our particle is greater than the electric field divided by the magnetic field, if it's faster than this speed, is it going to travel and veer off to the left, or is it going to travel and veer off to the right? It won't go in a straight line anymore, right? It only went in a straight line before because the magnetic and electric forces were perfectly balanced with each other. Does the question make sense now? To the right? This is the one that's going to get bigger, right? It's going to arc off to a certain side. That's exactly right, yep. The question is which side? Is it going to be the left side or the right side? This force grows, right? The only difference is just particle. We got a bunch of particles. They're all streaming through here, right? And they all come in with a bunch of different random velocities. Some of them will be going, let's say 10 meters per second. Some are 12. So I'm just asking, what if you have a particle that has a velocity that's greater than the exact ratio here? Which one of the forces becomes bigger? Is it going to be FB or is it going to become FE? Which force is going to get bigger? So you can actually just look at these equations here. The force from the electric field is pretty much constant. It does not change. This is a fixed value. But the force from the magnetic field, it depends on velocity. So if you have a velocity that's bigger than the one that allows you to go in a straight line like this, and then continue straight out here, if your velocity is bigger than this, can you see that this force gets bigger? So the net force acting on the particle is to the left, which means that particles that move faster are going to kind of come in here and they're going to veer off this way. And particles that are slower, if they're slower, let's represent that at like kind of a polar. If they're too slow, then the electric field's going to be bigger, right? And they'll go off to the right. Does that make sense? It's kind of confusing because they just introduced the idea. So, do you guys kind of okay? You don't have any questions about the velocity selector? You'll see this phrase show up in your homework, right? It'll say velocity selector. Really, all you need to remember is just this idea here, that this is like the Goldilocks speed, where it's just the right speed to allow the particle to travel in a straight line because the two forces are perfectly balanced like that. What if it was a negatively charged particle? Would this work for negatively charged particles too? What if I replaced it with an electron? Would that change anything? What would be the opposite? That's a good way of putting it, Tyler. Because the charges cancel, yeah, there's no difference. But you're right, Meowers, that these would flip. The electric force would be to the left, the magnetic force would be to the right. Yeah. But at the end of the day, it's the same thing. So if this works on a positively or negatively charged species, you just get all the particles that come out here all exactly have the same velocity. And that's really powerful if you think about it, is that you know exactly what their velocities are, and you can tune them. You can tune it to give you exactly the velocity that you want coming out of here. Okay, so that's the velocity selector. And a further application for this is called a mass spectrometer, and it kind of starts with the velocity selector. So the next thing we'll talk about is a mass spectrometer. Is this something y'all have heard of before? Or have you used these maybe, or heard of them in your other classes? like in your chemistry classes? Okay. Some people might have, I bet. What about the... You've just heard the name, okay. So here's what it does. It's remarkably simple, but just a little tricky to understand. So we start off with the same picture we had before. So we start off with a couple plates. One plate there, another plate here. Okay, that's not perfectly straight, but I think you guys can deal with it. One plate's positive, just as before, and one plate's negative. Okay. We put the entire thing into a region of space where we have a magnetic field that points into the board. So we have magnetic field going into the page. I probably don't really need to draw this many X's, but the idea is you've got a magnetic field. It points into the page. Again, we also have the electric field. I'll just draw a couple lines for the electric field. But there's our electric field. Again, we put a little thing at the end so that particles can only come out like through some center piece, and then we stream particles into here. So we say we have, now here, let's say we have some concentration of all kinds of different particles. Maybe some positive particles, maybe some +2 charge particles, maybe just all kinds of different particles, and we stream them all through here, right? Now, we know from before that any particle that manages to make it through is going to have a certain velocity. And that velocity, we said, was going to be equal to, I'll just scroll back up, it was the electric field over the magnetic field, right? So whatever the magnetic field is here and whatever the electric field are here, we know that the velocity of our particles when they come out of here are going to be equal to E divided by B. Now, to mix things up a little bit, let's say that in this region of space up here, there's a different magnetic field, and that we kind of have a big, long kind of detector plate right here. And the detector plate is just going to register if a particle hits anywhere along this location here. Maybe it could be phosphorescent, and it could glow, or something like this. But in the other region of space, where the detector plate is, there's going to be a different magnetic field. So there's going to be a magnetic field in this region, and that magnetic field is going to come out of the board. And maybe we call this magnetic field B prime, but this one comes out of the page. That means it's coming towards you. That doesn't look very good. Okay, so you've got magnetic fields, and it's coming out towards you. All in this region here. Okay, so two separate magnetic fields. This region where the velocity selector is, there's just this inward magnetic field, and here we have this outward magnetic field. So now, if we have a positively charged particle, I should extend this plate so it can go both ways, actually. If I have a positively charged particle that comes out of here, what's the direction of the force on that particle going to be when it comes right out like this? What's the direction of the magnetic force on this particle going to be? Again, you can use the right-hand rule. Point your fingers in the direction of the velocity. Curl them to the magnetic field. To the right, yeah. This is a force to the right, and now we've kind of reestablished velocity vector this way, force vector exactly perpendicular to it, and as a result of that, we know what kind of path this is going to travel along, right? It's going to travel along a circular path until it eventually impacts the plate right here, and the radius of that path, r, we know, is going to be equal to the mass of the particle, whatever it happens to be, multiplied by the velocity of the particle, divided by the charge of the particle, and then divided by the magnetic field in this region here, which is going to happen to be B prime. Now, what if the particle had the same mass as this particle, but let's say it has twice as much charge? So let's say I have this particle and I give it a charge +1, and another particle comes up through here and it has a charge of +2. What kind of path would the +2 charge particle take? So we'll say this is for a +1 particle. It's going to be a tighter radius. That's exactly right, because this number, if it gets bigger, the radius gets smaller, right? So if it's a +2 size particle, the radius should be how much smaller? exactly. We'll use, I don't know, this color maybe. So if I have a particle that has double the charge, then the radius is going to be half the radius. So this would be a +2 particle. So what this thing can do is it can separate species in terms of their charges. But that's not the only thing. It can also separate things in terms of their masses, right? Because the bigger the mass, the bigger the radius is going to be. It's going to have more inertia. It's going to carry it farther before it hits it. Does that make sense? So it'll separate all these species out. And if we had a negatively charged particle, it would go the other way, right? Negatively charged particles would fly off over here and land somewhere off to the left. This would be a negatively charged particle. And maybe another one for like a -2 particle. So it separates out particles based on their charges, but it's really separating them out based on m over q. And that's because the radius itself is given by mv over qb, but we learned from before that the velocity of the particles that were coming out of here is equal to e over b. So it's basically going to be m. Velocity is e divided by b. So you'd have m divided by q times b, and then times b prime. That would be your real radius right there. And all of these things would be something you could control. Like this would be something you could control. This would be something you could control. We actually saw a little bit today from that video, right? How you might actually be able to control this magnetic field. It's something that we're going to talk about more next week. But basically, by manipulating electric currents, you can have a very strong control over the size of the magnetic field you're using. So this is controllable. This is controllable. And this is controllable. And then R is something you can measure. You measure the radius on your detector here, or you know the information about the detector from wherever you bought it or whatever, and then it just spits out the number of particles that hit at different points. Anyway, so that's a mass spectrometer. We'll do a problem with this. Does anyone have any questions? It splits things up based on their mass and on their charge. So it could tell you, for example, like you've got some chemical here and it's got unknown, has unknown mixtures of different like elements or something like that. If you could ionize this particular mixture, then you could split it up based on those ions. And I believe that these things can often tell you what the chemical makeup of a molecule is, I think. Because let's say you've got a molecule and you don't know this is where I might completely get this wrong. You don't exactly know what the compound is. If it has, like, let's say 2 hydrogens and 3 sulfates, or if it's 3 sulfates and 1 hydrogen or something like that, it's going to split them up, but it's also going to have a number of hits, if that makes any sense, that can then be plotted out into a graph where it's like, okay, so many things hit here, so many things hit here, so many things hit here, and you plot the radius versus the number of... Actually, usually they plot the diameter, actually. Versus the number of hits, and it might be like, oh, so many hit at this point, and so many hit at this point right here, and maybe a bunch more hit here or something like this. And you use that to like find something about like the ratios that are within the mixture. Does that sound like what a mass spectrometer does to you guys? Maybe I'm getting it wrong, but this is from talking to students in the past. This is what I understand. I haven't used one of these in a long time. No one's saying anything. Did I lose you? It's okay if so. You're good, you think? Kind of sounds familiar. Sure. Wow, that's something like that. If you want to read more about it, you certainly can. Again, in physics, we're more interested in how it works, right? Instead of, like, what you use it for sometimes. Yeah. So, I believe... Yeah, here we go. So here's a problem. The mass spectrometer problem. It's a lot of words, but this problem is really quite simple. See if I can keep it so that our equation's up here still. Okay, so it says finding leaks in a vacuum system. Really simple. There's almost no helium in ordinary air. We talked about this in my Physics 1B class because helium moves too fast. And it's really light. So helium sprayed near a leak in a vacuum system will quickly show up in the output of a vacuum pump connected to such a system. They're saying if you put helium near a leak, it'll show up in the output of a vacuum connected, essentially. All right, so you're designing a leak detector that uses a mass spectrometer to detect helium plus ions, which have a charge of this and a mass of this. Ions emerge from the velocity selector with a speed of this, so this gives us our velocity selector speed. Velocity is equal to 1 times 10 to the 5th. They're curved in a semicircular path by a magnetic field B prime, so this is going to ultimately be, I believe, what we're finding here. And are detected at a distance 10.16 centimeters from the slit. The slit is going to be this slit right here. And so they're detected at distance, we'll just call that distance, I don't know, delta x or something, of 10.16 centimeters. So that distance is going to be the distance from here over to wherever it hits, basically. Okay. And our goal is to calculate the magnitude of the magnetic field B prime. So we're going to use this equation, because we've already been given velocity, mass, charge, and I'll show that we've given the radius too. Okay, so let's look at the way this is worded. It says they are curved in a semicircular path, just like what we have up here, by the magnetic field B prime, and are detected at a distance of this from the slit. So how is this distance going to be related to the radius of the path? They're giving us the distance from here to here, right? What is that distance for the circle? It's the diameter, right? Yeah. So this would be equal to double the radius, then, yeah? Alright, so we know what the radius is. We're trying to solve for B prime. So from this equation, B prime is going to be equal to mass times velocity divided by charge times the radius. Okay, mass is this. Velocity is 1 times 10 to the 5. And then divide by charge. And then radius is half of that, which would be about 5.08 times 10 to the negative 2 meters. So for this, then we get that B prime is equal to y'all can calculate that if you want to. I'll tell you what you get. We'll compare with what I get. Okay, what do y'all get out of that? I got something like 0.08 something. Does that sound right? Yeah. 0.082, we'll say. 0.082 Tesla. This is a very small magnetic field. Doesn't take a large object to make that, so supposedly this could be a very compact device, I guess, because the size of the magnetic field needed is really small. All right. Anyone have any questions? So that is a couple of applications of the electric force and the magnetic force kind of working together. There's 2 more that we're probably going to talk about next time if we have time. One is the measurement of the electron charge to mass ratio that Thomson did. The other thing would be something called a cyclotron. A cyclotron is a device that's used to accelerate charged particles. I'm going to leave that until next time, though, because I wanted to teach you at least one thing that would be helpful for a large portion of your homework problems, which is the force on a current-carrying wire before we go. It should be pretty quick that we can get through this, and we probably will have time for one problem real quick. Not this stuff, though, unfortunately. We'll have to talk about that next time. We'll have to talk about motors and torque next time. which makes sense. This is a pretty big chapter. My memory from teaching this in the past is that we often have to spend multiple weeks on this particular chapter. All right, so force on a current carrying wire. Would you prefer to see the math first or the demo first with this? Okay, the math. Yeah, he's going to use the math in a way. So, okay, so say that I have a wire. And let's say that this wire, I actually kind of have to make it somewhat... No, I don't have to. I've got a wire. I tell you that it carries a current I that goes in this direction here. And I tell you that the length of my wire, I'm going to use the vector L to represent the length of my wire. And we'll say the length vector points in the direction of the current. So the question here is, what kind of force would this wire feel if it was embedded into a magnetic field? So let's say that in some region of space or around the wire, that this entire wire is embedded into a magnetic field. And let's say that that magnetic field points, let's say into the page. That'll work, right? Yeah. Okay. We know that we think of electric current as being composed of little tiny charged particles that are moving, right? And one way we talked about it was we said you can kind of consider all of these charged particles here as if they're all flowing with kind of on average with a speed that we call the drift velocity, Vd. Each one of them carries some charge Q, and then we said when we dealt with this kind of stuff that imagine that we also knew what the cross-sectional area of our wire was here too. Okay, if that's the case, and we know how fast the particles are moving, and we know something about the charge on the particles, then we've learned that there's this thing called the magnetic force that would act on them, and that force would be equal to whatever their charge is multiplied by their velocity, which in this case would be Vd. This is going to be for one particle, and then we cross-product that with the magnetic field. Oh, I forgot to mention that. This is the magnetic field B. You'd cross-product this with the magnetic field B. Like that. This would be force on one charge. What direction would it point, quickly, in this case? On this particle here moving to the right, it'd go up. That's exactly right. So the force is up. But then if you've got a whole bunch of particles, right, the net effect is that the entire wire is actually going to feel a force because the things are in the wire, right? And if all these little tiny charges start to feel a force at the same time, certainly the wire is going to feel a force, right? And that's what we want to investigate. So to find the force on the wire, what we want to do is say that it's going to be equal to the force magnetic on the wire is going to be equal to, well, we've got a ton of these particles. In fact, when we talked about this before, we said we can use the symbol little n to represent the number of charges per unit volume. And then we'd say, if I know the number of charges per unit volume, and I multiply that times the volume of my conductor, which in this case is A times L, right? Then that gives me the total number of charges, right? And the total number of charges per unit volume was something that was related to the molar mass of the objects and the number of particles that were given up, number of free electrons that were given up, and all that kind of stuff. But this NaL would give me the total number of charges. If I then multiply that times the charge on a single charge carrier, and then multiply by all the rest of the stuff, this whole thing together would give me kind of like the total charge, maybe? You might think of it as like the total charge of the free electrons within the wire. And if we have the total charge, and we know that they're all traveling at this drift velocity, then if I take the drift velocity then, and I multiply by the magnetic field, I'm going to get the net force acting on the wire. Well, the thing is now that we've already said that the drift velocity is to the right, but what I really want to do is I want to pull the velocity vector off of this, and I want to put it onto the length vector here, now that we have it. And then I'm going to pull together the terms n times A times Q times Vd. Those are all going to come together, and then we'll have what's left over is going to be the length of the wire cross product with the magnetic field. Like that. That's going to be the force on my wire. The force on the wire is what we're trying to do. If you remember, and you probably don't, this quantity here, where I take the number of particles per unit volume, and I multiply by the drift velocity times the area of the wire times really fundamental electron charge. What did this quantity end up being equal to? Does anyone remember? Let's go way back in your notes. It's amps. It's current. Yeah, you can just work out the units and you'll realize you get that the units of this are current, if that helps. Because this is number per volume. You're multiplying by A times VD, which has basically volume per second, and then you've got charge. So that all ends up basically reducing down to just the current. And then we get this really nice relationship, which says that the force on the wire is going to be equal to, and I'll drop the wire part now. This is going to be the force on the wire. It's going to be the current in the wire now. The faster the current, the bigger the force will be, multiplied by the length of the wire, and we treat this as a vector that points in the same direction as the current, cross product with the magnetic field. And so now you can do problems where you'd say, like, I've got a piece of wire and it's placed in a magnetic field, and I want to know what the force on that wire is going to be. It's pretty powerful. And we can demonstrate this. This is a demo that's pretty fun to do. It's a demo you might be able to do at home, actually. Conceivably. Alright, I'll turn the volume on too so you can hear what he says. Let's see. Change windows. Yeah, it's a big magnet, right? We've got one just like that at the school. Isn't that cool? I think that's cool. Alright, how do you stop this? Do you do this? Oh, I see, okay. Anyone, can you have any questions about that? I think you could do this at home. I don't know. I don't know, maybe I'm wrong. There's the autoplay slider on top. Oh, that's what's doing it, basically. Yeah, for sure. I'm gonna leave that on. I like autoplay. Okay, let's switch back to the other screen. Maybe do one quick problem and then we'll stop the stream. True quality. No, change windows. Okay, so back to here. Let's do just a quick problem. I'm curious, does that look like magic to anyone else when you see wires do stuff like that? Doesn't look like magic to anyone? Looks like magic to me. I know it's not magic, I know it's happening, but it still is. I mean, it's this invisible force that you really can't see, right? I mean, gravity is one example of something like that, but we're pretty accustomed to gravity always pulling things downwards. These forces, they can pull things in all kinds of different directions. Okay, so here's our problem. We have a straight horizontal copper rod. It carries a current of 50 amps. That's a huge amount of current from west to east in a region between poles of a large electromagnet. In this region, there is a horizontal magnetic field toward the northeast, going up into the east. That is 45 degrees north of east with a magnitude of 1.2 Tesla. Find the magnitude and direction on the force of 1 meter section of rod. And then another question afterwards. Okay. In this problem, we're going to use the equation we just derived, the magnetic force equation. All right, we're given current. We're given magnetic field. we're given the length. It's just the 1 meter section that we care about here. So you see that length vector drawn here. We see the magnetic field vector drawn here, which means we know the angle between the two of them. So this is pretty straightforward. You just take the current, you plug that in, 50 amps. It's the rate at which the charges are moving through. And then you multiply by the length, which is a meter. Multiply by the size of the magnetic field, which is 1.2 Tesla. And then we multiply by the sine of the angle between this vector and this vector. That's what the cross product tells us to do. This will not give us the direction. It'll give us the magnitude of the force. So sine of 45 degrees. And this, what's that going to be equal to? Let's see. I don't know. I have to just... That's too much to do in my head. Make sure your calculator's in degrees. I got 42. We'll agree with that? Something like 42.4 newtons. And then to find the direction, you need to point, well, what would it be? You have to do L cross B. L cross B. Point your fingers in the direction of L. Rotate your hand to B. From B to B. Or from L to B. What direction is that point? Out of the screen, that's right. There you go. Okay, second question is, while keeping the rod horizontal, how should it be oriented to maximize the magnitude of this force? And what is the magnitude of the force in that case? How's that out of the screen? So they're on the same plane? Okay, you got it? Okay. Yeah, this is all the same plane. I think that these lines going inward kind of make it seem like there's a third dimension there, but there's not, I don't think. Okay, so how would we, while keeping it horizontal, what exactly does that mean? How should it be oriented to maximize the magnitude? What do you guys think about that part? Oh, I mean, sorry, I have to scratch my eyes because we want to make it 90 degrees, right? Yeah, so we kind of want to orient it like that way, right? Yeah, get the magnetic field perpendicular to the current. So if we tilt our rod like that and like that, it would maximize it, and then the force would be we'd have a right angle right here, and then the force would just be 50 times 1 times 1.2, which would be like what, 60 newtons or something like that. Out of the screen. Okay, and that's where we're going to stop for now. Does anyone have any questions?